Hi, this is Mrs. Vrobel. This is part 3 of Electrons and Atoms. This is the colorful section of the chapter. So we talked about what is light, how do we describe it. We talked about the wave and the particle properties. We talked about the photoelectric effect with Einstein and Planck's theory of light. Now we're going to look at why do we get color from certain elements. And I just want to share with you, I have this really cool looking ring. And the question is, where do we get all this color from the light that we see? Now, if you look at the spectra that I have there, so we have sodium, we have mercury, we have lithium, we have hydrogen. And notice that there's different types of colors associated with each element. And this is what makes elements special, is they have what we call bright line spectra. So sodium has one yellow line out of the whole series of possibilities. Notice that mercury, which is below it, it's got essentially 5 different yellow lines, and then it has 2 blue and then a handful of violet. There's a big difference between the two elements because the electrons actually determine what kind of light we see. So depending on how many electrons a specific element has, it's actually going to give us a certain color. And you're going to do a lab, or you have done a lab already, where you look at the color of the elements. And there's an overall color, and then there's individual colors. And what you see here is essentially individual colors for that specific element. Notice that there's a arrow at the bottom here. So on the right-hand side of the spectra, these are the shorter wavelengths of light. Notice that as you go to the left, like orange or red, we're talking about longer wavelength. So you may have done this lab, or you may not have done this lab yet. What essentially happens is we take a gas discharge tube. So we fill up a tube full of gas with a specific element. And it can't contain any air, because if it does, it's not going to give us the correct wavelengths of light that we're looking for. There's essentially 2 slits, and the slits help to modify the type of light that's coming through. You need a prism, because the prism is going to bend the light depending on what wavelength of light we're talking about. And notice that we have violet light all the way down to red. And the NM stands for nanometers. So we're talking about very tiny wavelengths of light. So what happens is these specific elements, they have unique energies. Not every element has the same type of light. So this is the nice thing about elements, is we can actually get specific types of light coming from that element. And you have to have an electric charge. This won't work at a steady state. So what's happening is the electrons that are within that element are being probed, or I don't want to say stirred, but they're essentially being electrified and disturbed. And when they do, they give off a certain color of light, and we're going to talk about how you get that color of light. But with the bright line spectrum that I just showed you, there has to be discrete energy levels. Otherwise, we would see a rainbow of color, and we do not see a rainbow of color. If we saw a rainbow of color, that would tell us that the electrons do not occupy, if we saw a rainbow of color, that means the electrons occupy many different places within the atom. But we know that is not the case, because we don't see that in bright line spectrum. Okay, now what's happening in the discharge tube? So before we see the color, what essentially is happening is the electrons are in their lowest energy state. So remember how we had the Bohr model of the atom? We saw the outer orbits from outside the nucleus. we know that the electrons occupy space outside the nucleus. And when we do not see color, we know that these electrons are in their lowest energy state. And the lowest energy state typically is called the ground state. So whenever you hear the ground state, that means the electrons are in their lowest energy level. When we see the color, so you know how I showed you that ring that was giving off those different bright lights, we have to have some kind of instability. So what's happening is the electric charge is coming in contact with these electrons, or you could have other electrons, so you could have bombarding electrons, forcing other electrons to higher energy levels. So think of it like ladder. You have the lowest rung of the ladder, which is called your ground state. You electrify these electrons. They move up to a higher rung of the ladder, and they go into higher energy levels. And this is what we call the excited state. So we go from the ground state to the excited state. Now, it takes a lot of energy to go from the ground state to the excited state, and that's why it's unstable. When we see that color, we have to have a release of energy. So we see the color when those electrons return to their lower energy or the lower rung of the ladder. So as they're returning to the lower energy state, we see that color. And that color that we see actually uses up a certain amount of energy. And that's why we get different colors, is because the different colors use different levels of energy. I love this slide because in this slide, it actually gives you a really good representation of what's going on when we see the different colors from elements being excited with electricity or other electrons. So here we have three different colors. We have red, blue, and, red, green, and blue. You may notice that the way these colors are drawn, there's a different frequency to each type. So if you had to guess, which one has the highest frequency? Yes, hopefully you said blue. So notice that there's more squiggly lines with blue, therefore it's a higher frequency. Now, if frequency is high, so if nu is increased, what do you think happens to energy? Energy is increased. So on red, if you have a lower frequency, energy is going to be lower. And obviously, the green color is somewhere in between. Also, when you look at the energy levels, 3 to 2 to 1, this is actually not drawn to scale, unfortunately. There's actually a wider gap between 1 and 2 than there is between 3 and 2. They kind of drew it evenly spaced, but ideally the gap between 2 and 1 is big. So the energy level difference between 1 and 2 is much bigger than the energy level between 2 and 3. But anyways, notice that when you go from energy level 3 down to 1, this has the greatest energy level difference. Hence the reason why we see a blue color is it's a larger energy requirement than going from 3 to 2. Now, what does this mean? There's actually 3 series, and you will get to know these very well. There's what we call the Lymann series. Notice that the Lymann series is in ultraviolet. Can you see ultraviolet? No. However, I will tell you, I did come across one person who had cataract surgery, and she actually found, because of her cataract surgery, because they did something to the lens of her eye, she can actually see a little bit of ultraviolet. And that's very unusual. Not all humans can do that, but she did because of her cataract surgery. Notice that we typically see the visible light. So the Balmer series is something we can see with the naked eye. We don't need another instrument to tell us that we're seeing those colors, okay? However, the Paschen is infrared. What I would do is maybe make some flashcards for yourself, because you will have to know the difference between Lymann, Balmer, and Paschen, just to let you know. And notice as you go from ultraviolet to infrared, the energy decreases. if you go from ultraviolet to infrared, the wavelength increases, and then lastly, the frequency will decrease. Now notice that the bright line spectrum is only for hydrogen. Okay, so the Paschen, Lymann, and Balmer series only works for hydrogen. It's different for other elements. Okay, this is a representation of the lines for each series. These are energy levels. So for each series, we're talking about a different set of energy levels. So notice that at the top line, this is actually infinity. Okay, so the very top line is infinity. All of these energy levels eventually reach infinity. The closer you get to infinity, the more narrow the difference between the energy levels. So notice that, like I was telling you, that picture that you saw 2 slides ago, there's a big difference between the first and second energy levels. Okay, it's biggest compared to the other series of energy levels. So the Lyman series, we're talking about going from an electron dropping down from 2 to 1 all the way up to infinity. And then with the Balmer series, remember we can see the Balmer series, we can't see the Lyman or the Paschen. We're talking about energy level 3 down only to energy level 2, okay? So the first color of light that we see in the Balmer series is going from energy level 3 down to 2, and this is only in hydrogen. So all 3 series, we're only talking about hydrogen element. We can talk about energy level 4 to 2 and so on all the way up to infinity. And then lastly is the Paschen series. So we're talking about infrared. And we start with energy level 5 down to 3, and so on, all the way up to infinity. So like I said, you will need to know the difference between Lyman, Balmer's, and Paschen. Remember, Lyman is ultraviolet, Balmer is visible, and Paschen is infrared. Lyman, we're talking about the first energy level going from 2 to energy level 1, all the way up to infinity. Balmer, we're going from energy level 3 down to only energy level 2, all the way up to infinity. And then Paschen, we're talking about energy level 4 down to energy level 3, all the way up to infinity. Okay, now we have some equations that we need to worry about. This is the next series of equations here. This is the Rydberg equation. So there was a man by the name of Rydberg, and he came up with, this is nu, so this is frequency, equals some constant, and it's 1 over a squared minus 1 over b squared. Well, what is a and b? First off, this is the Rydberg constant. Okay, so you will be given this. You will not be asked to memorize this. And notice it's in hertz. Remember, hertz is cycles per second, or 1 over second, okay? A is essentially the energy level, and it's the energy level that the electron is dropping down to, okay? So this is the last energy level that the electron is going to occupy. B is the original energy level that it occupied. So this is the lower energy level, this is the higher energy level. And then lastly, we have Planck's constant. So you're going to be doing some energy calculations. And once again, you need to know the Planck's constant, and that will be given to you. You will not have to memorize that. Okay, let's do some problems. So I want to do the first 2 or 3 with you, and then I'll have you do the last one yourself. You need to know the frequency, the energy, and the wavelength. So the first one is line B in the Lyman series, okay? And I'm going to go back to line B in the Lyman series with you just so we can... Okay, so the Lyman series is this very first series on the left here, and they essentially want us to look at this series. So we're talking about energy level 3 all the way down to energy level 1. So we're going from 3 to 1. Okay, so I'm going to go to my problem set here. Okay, so our calculation, like I said, is going to be energy level 3 to 1. And we're going to use the Rydberg constant. So we're looking at frequency, and we're going to multiply it by K. K is 3.27. This will be given to you, times 10 to the 15th cycles per second. And then this is going to be multiplied 1 over A. Now, the 1 over A is essentially the first energy level, and that's going to be squared, minus the energy level that it left, which was the third energy level. Now, when I do this calculation, I should end up with okay, that's my Rydberg's constant. I get 0.888 repeating, okay? When I add those, when I multiply those two together, I'm going to get 2.91 times 10 to the 15th. And that's frequency, so it's per second. Now, if I want to calculate energy, remember E equals h nu. So this is Planck's constant, which is 6.626 times 10 to the 10 to the negative 34th, and that's joules per times second, times the frequency we just calculated, so 2.91 times 10 to the 15th per second. And when you multiply those two together, you get 1.93 times 10 to the negative 18 joules. So it's still pretty small. Now remember, if you were to add a negative 34 to a positive 15, it'll be approximately a negative 18. And then lastly, I want to do wavelength. So I want to take the speed of light, which is 3.00 times 10 to the 8th meters per second, divide it by the frequency, so 2.91, 10 to the 15th per second, and that equals 1.03 times 10 to the negative 7th. Okay, that's the first problem. All right, let's go back. Oops. Sorry, I have to go through my screen here again. Okay, that was the first problem. Here's the second one. Line D in the Balmer series. Okay, so I'm going to take you back to the Balmer series. Okay, here's the Balmer series. Oops, sorry. So in the Balmer series, I'm looking at this line. My end energy is 2, but my beginning energy is 6. So I'm going from 6 to 2. Okay, I'm going to go back to my screen here. Okay, so I'm going from 6 to 2. So you're going from transition 6 to 2, and nu is going to be the Rydberg constant, which is 3.27 times 10 to the 15th cycles per second. And then that's going to be 1 over 2 squared minus 1 over 6 squared. And when you multiply that out, you're left with 3.27 times 10 to the 15th cycles per second times 0.222 repeating. When you multiply that out, you're left with 7.27 times 10 to the 14th cycles per second. Then you want to calculate the energy. So E equals h nu. So 6.626 times 10 to the negative 34th joules per second times the frequency that you just calculated, which is 7.27 times 10 to the 14th cycles per second. And the energy is essentially 4.81 times 10 to the negative 19 joules. And then lastly, lambda. So lambda equals speed of light, which is 3.00 times 10 to the 8th meters per second, divided by your frequency, which is 7.27 times 10 to the 14th per second, and that equals 4.13 times 10 to the negative 7 meters. Okay, your last problem that you're going to do on your own is you're going to do line B in the Paschen series. So that's going to be energy level 5 to energy level 3. And don't be surprised if you see that on the video assessment.